Hi everybody, this is Mark Weitzman, and welcome back to my QFT blog. This will be the fifth one. Today we're going to cover we're going to continue basically what we calculated in the fourth blog. We're going to do the photon self-energy for a charged spinless meson. And we continue following the previous calculation. But this time we use the Feynman Rules for charged spinless meson. And instead of Pauli Villers, I'm sorry, I forgot to switch here. Instead of Pauli Villers, we use dimensional regularization. Coleman says something funny in his book about when he talks first about dimensional regularization. He said, "It's very hard to follow the arguments in these fields as to the correctness of it." He said, "Either the arguments are unbelievable or they're incomprehensible, or sometimes both." So unless you really read the papers by, I never know how to pronounce his name, Tuft and Veltman, who established dimensional regularization, it's really hard to accept all these things. We just use them. Apparently they work, and they're really a nice gauge invariant way of doing quantum field theory most of the time. I don't think they work all the time, but I think most of the time. Anyway, because it's so similar to the last calculation, I'm going to leave out a lot of the intermediate calculations. Last video ran to almost an hour, and this one I'm hoping to get done in half an hour. So to lowest order, the photon self-energy. And again, the notation for the most part is the same. Prime is usually the renormalized quantity. And we basically have three diagrams to calculate here. First, we have the photon with the meson loop. It's not a fermion this time. And we have indices mu and nu. We have k going this way. We have p plus k going on the top half of the loop. And we have k going out. We have p on the bottom half of the loop. And so that's very similar to the diagram we had last time, except we don't have to worry about the spinners. Makes everything a lot easier. Then we have a new diagram. This is sort of unique to scalar electrodynamics. We have a mu and a nu photon coming in, and then we have a Meson loop. This is a four-field interaction. P, the momentum in the loop is P. We have K. And then we have our counter term. That doesn't look good. And again, as before, we'll call this part the unrenormalized propagator, K squared. And this thing over here is our counter term. Okay. Now we use the Feynman rules. For these space-time dimensions. So I have minus I pi tilde mu nu k squared is equal to minus I e squared. There's no negative sign in front because we don't have a fermion loop. We have a scalar loop. ddp, because we work in d dimensions. 2 pi to the d. We have I squared, the scalar propagators, p plus k, mu, p plus k, nu, divided by p squared minus m squared plus I epsilon times p plus k squared minus m squared plus I epsilon. And then, so that takes care of this diagram over here. Now we have the that special diagram, which is plus 2I e squared g mu nu, the integral of dp over 2 pi to the d, and here we just have one propagator. And Coleman points out, I'm not sure I understood this 100%, I'm going to have to go back and review it, that there is no what's usually called like a dimensional transmutation factor for the coupling E, since we are using mass shell renormalization. Alright, for now we'll just accept that. So for the first integral, we follow the usual procedure. And this is like quite similar to what was done in the previous video. That's why I don't want to do it again. So first we combine denominators. Using Feynman parameterization. Then we eliminate cross terms by shifting the momentum integration variable. By the way, you're not always allowed to shift the momentum variable. Anomalies arise because you can't shift the momentum variable. But these integrals will all be regularized. That's why we're using dimensional regularization. So we can, in fact, do this. P equals P prime minus K. I'm sorry, XK. And then linear terms in P prime vanish upon integration. Then we replace things like P prime U, P prime nu by 1 over d. Previously we did 1 over 4, but in d dimensions we have to use d. G mu nu P prime squared. This just reflects Lorentz symmetry in d dimensions. I don't know why all these things keep popping up on me. I'm going to have to move to a better software. So then after we do all this, we get minus I pi tilde mu nu k squared is equal to e squared, the integral from 0 to 1 dx, the integral dd prime 2 pi to the d 4 over d g mu nu p prime squared plus 1 minus 2x squared k mu k nu. This is divided by p prime squared plus x 1 minus x k squared minus m squared plus I epsilon, whole thing squared. Then we have the tadpole term, minus 2e squared g mu nu integral of d dp 2 pi to the d 1 over p squared minus m squared I epsilon. Okay. And then there's standard Minkowski dimensional integration formulas. You can see these usually in the appendices to just any quantum field theory book. Sometimes they might show you the Euclidean ones, but you can easily turn those into the Minkowski ones. So we're going to use this basic formula. Oh. Oops, another mistake. Okay, so when we use this formula, we get all right. Now, this term over here, this first term, can be transformed by an integration by parts. And then you can combine all three terms using properties of the gamma function. You know, things like gamma x plus 1 equal x gamma x. And I don't see it's not that hard, but you can in fact do the first term. You can transform it by an integration by parts, and you're going to end up with, for the whole expression, why does it do that? It's unbelievable. God, I don't understand this software. It's just unbelievable. It loses some of my thing, and it's like I didn't do anything to make it do that. So after you do the integration by parts, first term, and then, which is this term over here, then combine all terms, we get So as before last time, we get we see a transverse expression. That's the g mu nu k squared minus k mu k nu, and the counter term diagram is just like last time. And we sort of write in the same way we did last time. And the renormalization condition is the same. So this implies, it's fairly easy to see, that E is equal to minus pi to the d over 2 E squared 2 pi to the d So finally, now this is in d dimensions, and basically we want to know what happens in d equal 4 dimensions. So we define d equal 4 minus del. And then we use basic identities that you can easily just derive. 1 plus del ln A plus order del squared gamma del equal 1 over del minus gamma. Gamma is that constant, Euler, Maserati, or whatever it is, constant. 577, I think. Plus order del. And then, so now we find order del. the renormalized photon propagator. This is amazing. I don't understand what's happening. I just keep losing, I don't know, the thing's overheating or something. It's just so strange for it to do that. I've never seen an iPad or the software misbehave like that. We'll have to write it again. Sorry about that. I think if I'm at the top, I do better. Might just be the new version of the OBS software that I'm using. I don't know. All I know is they finally fixed this date thing. I think you could see at the very top of the thing, it always used to have a weird date here. And now it finally has the right date and time. So they finally fixed that. Been waiting like 2 years for them to fix that. If anybody else has had similar problems with an iPad Pro, let me know. The good thing is that it's only losing like a couple of lines when it does that. So this is again, that's our final answer. This is again transverse, finite, and satisfies. As you can see, when we put k squared, when we have this, substitute that 0, we get ln, 1 minus I epsilon over m squared. Epsilon also goes to 0, so we get ln of 1 equals 0. So that's good. Okay, I just wanted to show you some long calculate. These are not really that long. If we did the electron magnetic moment, it would be like 3 times as long. But I just want to show you some calculations in quantum field theory that I'm reviewing on my blog in terms of Pauli Villers and dimensional regularization. Thank you for watching, and I'll see you next time. Bye-bye.